Okay, so last time I asked you to take some problems home, right, for homework. So I'm going to collect those now. You have those, just kind of get them together at your table and then make sure your name is on at least one page. Okay. Here, thank you. Thank you. Right here. Okay. All right. Anybody else? Do you work here? You do? I didn't know that. Okay. Anyone else? All right. So, what are we doing today? Well, I have an announcement first. We're supposed to take a test on Wednesday, next class. That's supposed to be exam 4. So I thought I'd run this by you. Exam 4, my idea for this one is to not have it. All right? So I'm thinking let's not have exam 4 because we're going to have a final next Wednesday anyway. And what I'll do is I will replace exam 4 with the highest grade out of all of your grades. So if you did well on exam 2, I'll just replace your exam 4 with exam 2 grade. Does that make sense? Okay. That should help most of you, I think. But there's just not enough. I want to cover some more material, and I don't want to eat up Wednesday with a test. So any objections to that? Okay, so exam 4 cancel. We will replace exam 4 grade with your highest grade. Which will include the final. So if your final turns out to be your highest exam grade, then this is why. No. Okay, so if your final exam turns out to be your highest grade, then that's going to be the grade that will replace your exam 4. All right? Okay. Hello. You're going to need a chair or something. Yeah. Okay. Maybe, how about the back corner? That way if you need to go out or something. Is that all right? Yeah. Okay. Okay. So, any questions on that? All right. So with the polynomial homework, were there any questions? Yes?
Yeah, when I got to x squared minus 4.
Yes. X squared minus 4.
Yeah.
Which one was this?
I think it was probably
Wait, which one? Sorry. Say again. Number 3. Number 3. Okay, let me get this one. Let me get my towel here. I got it. Okay. What's that? Nah, that's all right. It's good. Okay, so this one is f of x equals negative 3x to the 4th plus 24x cubed minus 48x squared. Okay, so for this, I'm going to just do the whole thing, okay, just in case you... All right, so the first step is to make sure that it's a polynomial function, which it is. Second step is what? The degree. The degree? Yeah. So we're trying to find the left and right behavior, right? So the degree of this is 4, which is an even number. That's what we're interested in, right? The leading coefficient is -3, so that's negative. And then working off the table, that means you're going to go down on both sides. And in the middle, we don't know, right? Okay, so far that's fine. Next step?
On the X-intercepts.
X-intercepts. So the X-intercepts here, we have to set this equal to 0. And so first step here was what, GCF? What did you pull out? Do you remember?
X squared.
Did you pull the -3 or just x squared?
No,
-3 and x squared? Okay, that's good. -3x squared. And then you're left with x squared, right?
Yeah,
Minus 8x plus, what's that, 12? 16 equals 0. Okay, and then on this one, you broke this one down. Do I need to show that work, or you get -4?
Yeah.
Twice? Okay. So 3x squared, and then x minus 4, x minus 4. Does anyone want to see that step from here to here? Anyone want to see that? Yes? We're okay? Okay. So now you are supposed to what? Set each of these equal to 0? Okay, so when we set this to 0, we get 0. Here we get 4. And here we get 4, right? Oops. But see, here's where you probably ran into the issue, all right? These are the same answer, right? And that means that we need to recognize this can be rewritten as a squared factor. This is x minus 4 times x minus 4, so that's x minus 4 squared, right? And that's important because when it comes to figuring out if you cross or you bounce, here at x is 0, you're going to bounce, right? Because this is squared. And then here at x is 4, you're also going to bounce because that's squared. If you do it here, then this will tell you, oh, you're going to cross, but then you're going to cross at the same place. You're never taking into consideration the fact that it's that repeat. It's a repeated factor.
What I kept doing is I kept try to redo it to make that 4 negative.
So it wouldn't. If you try and draw, it wouldn't let you cross, right?
That's what it is, yeah.
So let's see. If we try to do it this way, we would have an x-intercept at 0, and at 4. We know it goes down here and down here. We would think that we're supposed to bounce here, cross here, cross here. So we would be like trying to bounce off 0, and then we'd be trying to cross at 4. But then we have to get back here, right? Which means you have to go through the axis again. It's not going to happen. So it should bounce again like this. Okay? So I mean, lesson learned. Now you know on the test, you'll know what to expect there. Anything else? Okay, today we're going to move on to the next type of function, and the homework is going to be exactly the same as last time. I'm going to give you problems to take home, all right? So we're not going to do anything out of the packet for this assignment, all right? So we're going to move on to the next type of function. We've covered so far linear, right? We've got linear functions down. We've got quadratic functions down. We've got polynomial functions down. In fact, we learned that linear and quadratic actually belong to polynomials, right? So we learned last time. They're all kind of in their own category. So all these are very similar. But now we move on to the next one called rational functions. And these are by far the most difficult to do, all right? So in this class, I'm going to keep it kind of, I'm going to keep the difficulty level pretty low on these because they can get very messy, all right? So here's what a rational function is. Rational function is a function that looks like this. You remember what polynomials look like? Last class, I showed you polynomial. It was like a sub n x to the n plus a sub n minus 1 x to the n minus 1 plus dot, dot, dot. Remember that? And it was real ugly, and we talked about why we do it this way. Okay? For a rational function, here's what they look like. It's a polynomial divided by another polynomial. So it's one of these divided by a different one of these. All right? So you can imagine that that could be pretty complicated, right? So I'm going to give you a few examples, okay, just so you can see, and we'll look at them and say, yeah, that's a rational function. The word rational comes from the root word there, ratio meaning fraction, okay? So we are creating a fraction of polynomials. I'll show you what these look like in a second. We'll graph them. Before we do them by hand, I'll show you on the computer what they look like. But for now, let's just make sure we understand what they look like when they're written as a function. So something like, I don't know, 4x minus 8 over x squared plus, no, not 2x, x squared plus, let's go 8x. That is an example of a rational function. Is the numerator a polynomial? Look at the top. Is it a polynomial? Well, that by itself, if I told you that was a function, what would you tell me that is? Linear, right? Is a linear a polynomial? Yes, we talked about that last class. Is the bottom a polynomial? Yes, it's a quadratic, but all quadratics are polynomials, right? So this is a polynomial divided by a polynomial. And the question would be, what does this look like, right? If we graph it, how do we graph it? What are the steps? Okay, so that's one example. Let me give you another example. X squared minus 4x over x squared minus x minus 6. That's an example of a rational function. Polynomial on top? Yes? Polynomial on the bottom? Yes, okay. So this is a rational function. One last one here. Let's go 3x squared minus 27 over x. Is the top a polynomial? Yeah, it's quadratic. The bottom, that's actually a linear function. So it's just x by itself. So we do have a rational function here. Now, I want you to notice something about these three. I mean, I could keep going all day, right, and just keep putting different examples up. But I put these three specifically. I don't feel like I pressed record. Yes, I did. Okay. These three I put here specifically because there's something special about each of these three. So look at the first one. Can you tell me on the first one up here, what is the degree of the numerator? And the numerator, I mean the top, right? What's the degree of the numerator? 1. What's the degree of the denominator? Is 2, right? So would you agree in this particular case, I'm going to write it this way, the numerator, the degree of it, is smaller than the denominator. Do you all agree with that? The degree of the numerator is smaller than the denominator. Yes? Yes. Okay, what about the next example? What's the degree of the numerator? 2, and this one is also 2, right? Here, the numerator and denominator degrees are the same, right? They're equal. And in the last example, the degree of the numerator is what? 2, right? Degree of the denominator is 1, and that means it's bigger, right? Numerator is bigger than denominator. So I'm talking about degree over here, right? So I gave you these three examples because when it comes to polynomials, you can only have one of these three happen. Do you all agree with that? I mean, if it's a polynomial over a polynomial, each one is going to have a degree. So they're either going to be numerator smaller than the denominator, the same degree, or numerator bigger, right? Those are the only three possibilities. And believe it or not, those three different possibilities, we have to look at each one in its own way. So like when this top thing happens, we have the graph looks a certain way. If this happens, the graph looks a different way. And if this happens, the graph looks different. So there's a lot of different scenarios that can happen here, but these are the only three that we are going to have to consider. All right? Does that make sense? Okay. You all ready to look at a couple of these with the graph? Okay, ready or not, it's coming. Okay, so I think I'm going to do this using a website, this Desmos here. I still have that laser hair removal up there. Okay, let's do that first one. 4x minus 8 over x squared plus 8. Oh wait, no, plus 8x. There it is. Let me get this out of here. Let me zoom this out. And let me move it over here. Let's take a look at this one. Can you all see that? Does that look like a line? Does it look like a parabola? Maybe it looks kind of like a U, you know, but it's not symmetric. So it's not a line, it's not a parabola. Is it a polynomial? Remember polynomials last class? They look like this, right? And then like both sides went down or up, or you know, we had these different cases. But it was nice and smooth and curved, right? Look at this one. What's happening on this one is it looks like out to the left, it almost looks like it's kind of flattening out. Do you all agree with that? Let me get my mouse here. On the left side, the graph, I keep going out this way. Look at that graph. Doesn't it look like it's just getting closer and closer, like to the x-axis, just getting smaller and smaller? Do you all see that? And then as I come in the middle here, some weird stuff happening. Like the function starts to go, and then it just kind of just dives off. It just kind of falls away, doesn't it? And then all of a sudden, the graph reappears over here. It looks like a little U. But then over here, it kind of flattens out, and then it also kind of dives off. Do you all see that? That's kind of very strange looking function, yes? Okay, let's compare that to this one, all right? Let's see what this one looks like. So I'm going to type that one in now. And I'm going to leave them all up there at the same time, just so we can compare. So this one is x squared minus 4x over x squared minus x minus 6. And let me take the other one out of there just so we can look at this one for a little bit. So let's look off to the left there. Off to the left, does it look like it's kind of flattening out again? Does that kind of seem like it's flattening out? Right? Like it's not going like that and it's not going like this, right? It's doing something else. And then to the right, we have kind of that same effect. It's, instead of dropping off, it's kind of taking off, right? And then in the middle here, it's doing some weird little like S shape. And then again, here it looks like it flattens out and then it kind of drops off. Very strange looking function, yes? Okay. What about the last one? Does it already seem like this is going to be difficult to graph these? I mean, just by looking at them, they look like, how in the world are we going to come up with this stuff? Okay, 3x squared minus 27. But then divide that by x. And now let's take that one out. And let me zoom out on this. Look at this one. I mean, it's really hard to tell what's happening here. Does it look like it's flattening out as it comes out this way now? No, it looks like it's diving down. Then it looks like it goes up. And then all of a sudden, the new graph, it's like down and then up, right? So would you agree all three have very different sort of things happening? Yes? Okay. So how in the world do we graph these? Well, that's why you're here. I'm going to help you learn how to graph them. All right? So by the end of this, you should be somewhat comfortable, hopefully. All right, so let's kind of hit the pause button on this. I want to talk a little bit more about rational functions before we actually do this part, all right? So before we do this, I want to look at a different rational function and discuss a little bit about its characteristics, and then we'll attack those. All right, so when it comes to rational functions, one of the basic examples, most basic examples you can look at is this one. So this is kind of like your classic example of a rational function. This is like when you first start graphing lines, you get a very basic line, you take a look at it. This is kind of like your most basic rational function. So let's talk about some of the characteristics of this. I'm going to ask us to graph this, but I'm going to use the old school way, which is a t-table. Remember when you were asked to graph doing a t-table, like plug numbers in, get your input and output, and just plot points? Let's do that. Let's plug in some values of x and see what comes out for y. And remember, this is y. So someone give me a value of x. 1? Okay, I'll use 1. How about 1? 1. Plug 1 in, what do you get?
1.
You get 1, okay. So if you look at that as a point, that's the point 1, 1, right? So on my graph, it will look like I go out 1, I go up 1, I put a point, okay? All right, let's plug in 2. What happens if you plug in 2? 2. 1 over 2, right? 1/2, you get 0.5, right? So if I go out to 2, I go up 1/2, I'm right here. What's going to happen at 3? One-third, which is going to be a little bit smaller, right? At 4, 1/4. At 10, 1/10. At 100, 1/100th. At 1,000,000, 1 over 1,000,000, right? All of these are they're getting smaller, aren't they? So what's happening here is my graph starts to approach 0. Now, does it ever reach 0? Is there ever a number you can plug in here? Like if you keep moving out here, plug in 10, 100, 1,000, 1,000,000, 1,000,000,000, 1,000,000,000,000, will you ever get to 0? No. You're always going to have a little tiny number there, right? That's important to understand that the way that this function is behaving, you never actually hit 0 out here, ever, okay? So how do I somehow signify that this graph gets smaller, approaches 0, but never gets there? What we do is we put a dotted line out here like this, and we have a name for this dotted line. We call it the horizontal asymptote. Asymptote. That's a weird word. It's spelt weird. It's pronounced weird. A-S-Y-M-P-T-O-T-E. Asymptote. The P is silent. Asymptote. Horizontal, because it's horizontal. So I like to look at this dotted line. I like to look at it as like a magnet, right? A magnet that attracts your function to it. It pulls your function towards the dotted line, but your function never ever gets there, all right? Make sense? Okay. What happens if I start to go out this way? Instead, plug in some negative numbers. So what happens if I plug in -1 here? Well, 1 divided by -1? -1. What if I plug in -2? -1/2, right? What if I plug in -3? -1/3, right? And then -1/4, and -1/5, -1/10, -1/100th. Keeps on going, right? So these values on the other side, -1, -1, -2, -1/2, they're getting smaller, getting closer to 0, but they're all negative. So it's going like this. And it again is getting pulled towards the horizontal asymptote. Do y'all see it? So this idea of a horizontal asymptote is something that appears in rational functions. It doesn't appear in polynomial functions. It doesn't appear in quadratics or linears, this idea of a horizontal asymptote. But with rational functions, sometimes, not all the time, but sometimes we do have these, all right? So a horizontal asymptote I want you to look at as a dotted horizontal line that pulls your function towards it, all right? Do you remember in the last polynomials we talked about left and right hand behavior and we used that table to figure out that thing, right? That's no longer in play here. Okay? You can't use that table for these because these are rational functions, totally different. So when we talk about left and right behavior for rational functions, we have to use the idea of the horizontal asymptote. We either have a magnet pulling our function or we do not. All right? So this is, I'm going to give you steps, don't worry. But I just want you to geometrically understand the idea of what they look like. Do you all kind of get it? Okay. Now there's something else very interesting happening here. I have conveniently avoided plugging a certain number in here because it's bad. What number is really bad that I cannot plug in here? 0. I can't plug 0 in here because I do 1 divided by 0, and 1 divided by 0 is undefined. Right? Undefined. So that means if I try and plug 0 in, there is no dot, right? There is no dot here. There's nothing. Plug 0 in, nothing comes out. Undefined. We have not had this happen yet. When we graphed lines, when we graphed quadratics, when we graphed polynomials, we never had a point we couldn't plug in. Now we can. That can happen, all right? But what's even more interesting is what's happening near 0. So let's talk about what's happening near 0. What if I try and plug 1/2 into this function? So what would happen if I plug 1/2 in here? What's 1 divided by 1/2? It's 2. This is 2. Because this is 1 divided by 1/2, which is the same as 1 times 2 over 1. Remember, division is multiplication of the reciprocal. And then this is just 2, right? So at 1/2, I go up 1, 2. All right. What if I plug in, let's say, 1/4? Go ahead. If I plug in 1/4, where will I be? 1 over a fourth would be 4, right? So that means if I go to 1/4, I'm up here at 4. Alyssa? What if I plug in 1/10? Plugging 1/10 into this. So when we plug in 1/2, we got 2. When we plug in 1/4, we got 4. If we plug in 1/10, what are we going to get? 10. It's just the reciprocal of it, so it's going to give us 10, which means 1/10 is like really close, isn't it, to 0? And it's going to spit me up way up at 10, right? Could I get even closer to 0? What's a number that's even closer to 0 than 1/10 was? 1/20th. What's even closer? 1/1,000,000th? Yeah. Do you believe that there is a number right here, 1/1,000,000th, that's really close here? I'm assuming. It's there, right? I mean, this is a number line. There's every number's in there. So if you plug in 1/1,000,000th, you're really, really close to 0. What would it spit out? 1,000,000, which is way up there, right? So what's going on here with your function is your function is exploding, right? It's blowing up right here. It's approaching infinity, isn't it? But remember that at 0, what was the answer? Undefined. So we never actually get here. So I'm going to draw a dotted vertical line this time, like this. And this, guess what they call this? The vertical asymptote. That is a very strange function, isn't it? Like as you go out this way, it's getting pulled towards this dotted line. But as you start to get closer to 0, which is where the function is undefined, your function's like trying to go, just trotting along. Then it's like, shit. Oh, wait. Oh, sorry. Sorry. It's like, you know, I got it. And it's almost like this imaginary wall, right? And your function just has to like pull up and just take off, right? And it just can't ever hit that wall. Just explodes. Understand? Now, what happens on the other side? How about if we try and plug in -1/2? -2. So at -1/2, we're down at -2. What happens at -1/10? -10. -1/1,000,000th. -1,000,000. So it's doing the same thing, but opposite on the other side, isn't it? Like that. Make sense? So, looking at this function, this rational function, is a good example of a function where you can see what horizontal asymptotes are and vertical asymptotes. Does this function have X intercepts? Does our graph ever hit the x-axis? No. This one doesn't, but we actually can have rational functions with X intercepts. The reason you know that is because I just graphed them for you a second ago. Did that one have X intercepts? You had it right there and right there. Let me bring up this one. Take this one out. Close that out. Sorry, I'm trying to look at this one right here. Do you see the x-intercept on this one? There's an x-intercept here. So just because it's a rational function does not mean it doesn't have x-intercepts. It could. It might. You'll have to determine that, all right? Now, we're about to get into the steps, but I have a more profound question for you, and that is, when would these functions ever be used in the real world, right? I talked about linear functions are good for modeling, like, you know, you work hourly wage or something like that, you get paid some commission, some percent of what you sell. Parabolas, we were throwing things around the room. I talked about, you know, bombing people and stuff, and parabolas and cell phones. So I think I convinced you that quadratic functions were useful. Polynomials, I showed you that you could use those like stock market, anything that fluctuates up and down. But what about these? When are these important? So let me ask you a question. I have a movie quote. Let's see if anyone can name the movie. All right? You ready for the quote? Extra credit, yeah. Well, as time has gone on and I've gotten older, less students have known this quote. We'll see. Okay, here it goes. On a long enough timeline, the survival rate for everything drops to 0.
Mission Impossible.
No. Good guess. On a long enough timeline, the survival rate for everything drops to 0.
Back to the Future.
No. Not that old. Okay, let me draw what's happening. Time. Survival rate. Wait a minute. VA. Okay, survival rate. On a long enough timeline, so if this timeline is long enough, the survival rate for everything drops to 0. Which means that if you graph this, it drops to 0, but never actually gets there. That's not helping with the movie quote. I'm just trying to get you to understand what they're saying, what he's saying in the movie. No?
Matrix.
One more try. Matrix, no?
Jurassic Park.
No.
Lion King.
Fight Club. Have y'all seen Fight Club? Anyone seen Fight Club?
Oh, no, I actually haven't.
Ed Norton Jr.? Brad Pitt?
Yeah,
Who has seen Fight Club? That's it, huh? Okay, well, so I was actually talking to someone about this just the other day because my niece had a recall on her vehicle. It was an airbag recall. So they sent her a thing and it said, hey, you need to bring your car in, we'll replace the airbag because they were manufactured incorrectly and they could explode and basically kill you. All right, is what the recall was for. So she was asking me, she said, well, you know, does that mean everyone who has this car is going to get their airbags replaced? And I'm like, yes. And the company's going to pay for it. In this case, it was Honda. Said anyone who had that airbag installed by that company that's defective, they will have their airbags replaced for free. She's like, well, isn't that expensive? And I said, absolutely, it's expensive. But we started talking about what this movie, the guy who is in this movie, he works for an insurance company, and basically the idea is this. The way I explained it to her is, let's say you have 100,000 of these cars out there, right? Okay, so imagine there's 100,000 cars. It's probably more, but let's just take that nice number. 100,000 cars that are defective. Now, the insurance company will figure out, or the company that manufactures the cars, the people who are going to pay for this will say, what's the probability that it's going to fail, that they're actually going to have someone die of this. So maybe they figure that it's going to be like 0.1% failure rate. Okay, failure. So we multiply that by by 0.1%, which is 0.001. What would happen if you multiply that by 0.001?
Oh, okay.
Go ahead, you can. It'd be nice if y'all were being interactive here. I don't expect that you would do that in your head. You're basically dividing that by 1,000, so 100. Okay. So does everyone understand this? They have this company has 100,000 of these cars out there. They figure that about 0.1% of them are actually going to have a problem with the airbag, and that means 100 cars, right? 100 cars that they can count on are going to have problems. And the company will then say, let's assume that those airbags in those 100 cars kill those people. Sorry, this is not a PG-13 class. So imagine that 100 of these cars kill the driver, okay? Then that's 100 lawsuits you have to settle, right? How much do you think you're going to pay out to the families for each lawsuit? $1 million? Okay, so that's going to cost you $100 million, right? $1 million for each family. Okay, they look at that number, and then they say, okay, let's take these 100,000 cars, or what was it, 100,000 cars, right? And I just went to $1 million, didn't I? Sorry. They say, all right, let's take 100,000 cars. Wait a minute.
Wait, you read $1 million?
Yeah, I'm lost. Okay, 100,000 cars, and they say, okay, how much will it take us to do the recall, to bring them in, pay the people, the labor, all that, right? How much is that going to cost per car? So I looked at the receipt because I asked if I could see. They gave me the receipt. It was 0. I said, can I see your receipt that you're going to submit to the company? And our recall, it was going to cost them total 600. It was like $600. Okay? So what's 100,000 times $600 each? So what would that be? We're just going to add 2 zeros and a 6 to this.
60 million. Right there. 60. Yeah, 60 million.
So 1, 2, 3, 4, 5.
Times 600, right? Yeah.
60 million,
Yeah.
right? What are you going to do?
Yeah, 60 million.
You're going to do the recall, right? Now, if this number is smaller than that number, they don't do the recall.
So what if all the cars go out?
What's that?
What if all the cars go out?
Well, that's why this number is so important, the probability of failure, right? Because they need to make sure this is right. I know it's not, look, now there are some other factors, like we're talking about people possibly dying, then there's other government agencies that get involved and say you have to do the recall. But when it comes to things like, you know, things that are just maybe going to hurt people and not kill them, then they decide, you know. We can pay these families and everyone will be happy on this side. Or we pay, imagine if that was like, you know, $6 billion, right? Then you say this is the obvious choice, right? Hey, okay, so this movie Fight Club, the guy who, he works for an insurance company, he tries to explain this in one of the scenes. But he says that he uses this quote, on a long enough timeline, the survival rate for everything goes to 0. So forget that whole insurance thing, that was just me yapping. This right here, what does this mean? It means that, well, just think about humans, right? Think about human beings. Just on average. Let's say that this is time 0. Let's say you're born healthy. A healthy human being is born, right? The probability that they are basically alive is pretty good, right? Okay, so let's say the probability, if you're born, let's say you're born and you're born alive. Then we're going to say that you are 100%. You're 100% alive when you're born, okay? Now, what happens as time goes on? The probability that you're going to live to a certain age is going to start to decline, right? Now, what's the probability that you're going to live to your 20s? On average, let's say American, you know, pretty good, right? Pretty good. We're all going to make it to our 20s, right? Pretty good. Probability that you're going to make it to 50. Still pretty good? Yes? Yes? No? No? Probability that you're going to make it to 75. Now you start saying, are you a man or a woman, right? Because there are differences in lifespans of men and women. So 75, do you still think that the probability is there? There's some probability that you're going to make it to 75. Yes? How about 100? No. What do you mean by no? So we're saying, is there a chance that you could make it to 100? Yeah. Last weekend, I was at my wife's grandpa's 101st birthday party. Okay? The man still drives. Now, he doesn't drive well, but he still drives. Okay? He's functioning completely fine. I can have conversations with him about McLaurin series, Calculus 3 topics. He's all there, right? Very smart man. 101 years old. Okay, so would you agree that your chances of living to 20 are much better than to 100, right? How about to 110? What's the probability of living to 110? Not as good, right? How about to 200? What's the probability that you'll live to 200? Not possible? No one's done it, but does that mean it's impossible? So what we start to do here is this probability starts to get very, very small, right? But we're talking about really small. No one's lived to 200. But what you cannot say is that it's not possible. To say it's not possible means you need this to go to 0. Like it needs to be 0, right? Like 0 probability. But this model of this function that drops down and gets closer and closer to 0, do you see how this models the real world, the probability of someone living to a certain age? Now, when I say this is small, I mean really small. What do you think's better in terms of probability? Do you think the probability of you living to 100 or winning the lottery? Which of those probabilities do you think is bigger? Just curious what you think. Like if you play the lottery at certain times in your life, what's the probability of winning the lottery versus living to 100? What do you think's better? Do you think living to 100 is a better probability? I think that is too. All right. Now, how about living to 200? What do you think? You think the odds of living to 200 are better or worse than winning the lottery? Probably worse, right? But is it possible? Yes. So maybe this probability right here is like the probability of you winning the lottery every single time you play it. Could it happen? Yes. Could, right? It could, right? If you no, I'm not saying can't, like will you? Can you? You can, right? If you go play the lottery every single day of your life, you could win every single day. Now the probability is like infinitesimally small, but that's what we're talking about here. Infinitesimally small probabilities. Or like the probability of getting hit by lightning and surviving 5 times in a row. Like, you know, I mean, these probabilities are infinitesimal, but they exist. So these functions, these rational functions, are really good at modeling things like where you have something that's kind of decaying away but never really going to 0. You can look at things like the lifespan of a light bulb, right? You buy your light bulb, you put it in, probability that it works in the beginning, pretty good. But then over time, you know, one of those days you're going to flip the light switch and it's not going to work, right? But you can't say exactly when. You just know that it's got some sort of curve that shows about how long it should go.
Do nations use that to explain kind of like mortality rate and birth rate of like each country or each state? Or count like the population?
Yes, we use a different type of function. We use a different type of function to do populations. Usually they're exponential functions, which are after rational functions. We talk about exponential functions. But they have the same characteristic. They all have a horizontal asymptote, where the graph starts to dive down. You also can have it the other way. You can have, like, just looking at population, you can look at population growth. So you have like a population that's growing, but then it has like this cap, this ceiling where it can't get past it, because eventually your population gets so big that you don't have enough resources to support the population. So there's kind of like a max you can get to, right? Like eventually it's like everything's great, and then what, you start running out of food, you don't have enough electricity and water, and like you just can't get past a certain critical point. Does that make sense? So we use these types of functions for that. But see, you can't do this with a linear function. You can't do this with a parabola. You can't do this with a polynomial. You have to have this horizontal asymptote for those types of problems. Okay, so I'm just trying to show you that rational functions allow us to look at different types of things that we weren't able to look at before, all right? And now let's just get to what is most important to you, which is how to graph these, all right? So you all ready for the steps? All right, here we go. How to sketch rational functions. What do you think the first step is? Make sure it's rational, right? So first step, make sure it's a rational function. Do you all remember me having that conversation with you about like why are you in school? Why do you have to take these classes? I told you like an employer is going to hire you and they don't want to have to teach you how to use the copier like 5 times. Do you remember me giving you that analogy? So we got new copiers the other day, and I got it pretty quick. I was ready to. That was it. I got it. I learned it. It was pretty fast. So I am teachable. I'm learnable. Okay, second question. But I'm just thinking about all these steps I'm about to give you, and you're sitting there going, why in the world do we need to know this, right? It's about a process. Can you follow a process? Here it is. Rational function, yes. Next thing we're going to find are the X intercepts. Now we did this with polynomials, didn't we? Yes. We're going to find the X intercepts. And I'm going to put after this, if we have them. We don't even know if we do. Okay, we may not have x-intercepts, all right? Here's how we will know. What we will do to find the x-intercepts is we will set the numerator equal to 0 and solve. So there's a very simple way to figure out where this graph hits the x-axis. You just look at the numerator and you set it equal to 0. Okay, so you're going to have to solve an equation. Simple enough? Okay, third step. We're going to find the VAs, which stands for vertical asymptotes. Again, if we have them. If we have them. We may not have vertical asymptotes. So what were the vertical asymptotes again? Those are those things where your function was going as like this wall. It was like, whoa, and it had to like go up or down, right? Okay, we need to find those. And the way we find those is by setting the denominator equal to 0. And solve. So far, to graph these things, we've had to solve 2 equations, right? That's it. Just solve 2 equations and we're on our way. Solve that equation, we've got x-intercepts. Solve that equation, and that tells us anywhere where we have vertical asymptotes. Now, here's where things start to get messy, all right? The fourth step is to find the horizontal asymptotes. If we have them. We may not. Would you all agree step 2, finding the x-intercepts, is something you've done? You've set things equal to 0 and solved before, right? Step 3, set something equal to 0, solve. You've done that. No, this is not anything new. Step 4, this is new, all right? What we're going to do is we are going to compare the degree of the numerator and the denominator. I'm just going to put num for numerator and dem for denominator, right? We're going to compare the degrees. And how many different cases did I say we would have when you compare the degrees of the numerator and denominator? 3, right? We are going to look at each case now. What happens in each case, all right? So case, I'm going to call it case A. Let's say the degree of the numerator is less than the denominator. That means the top one is smaller than the bottom one. In this case, the x-axis is the horizontal asymptote. I'm going to go through each example. I'm going to give you an example of each of these cases, so you will see what I mean by that when we get to it, okay? Case B. The numerator is bigger than the denominator, the degree. In this case, you have no horizontal asymptotes. You don't. You have none. None, okay? No horizontal asymptotes. Which means for us this. This is important. If we don't have a horizontal asymptote, if we don't have a thing that pulls our function down at the ends, that means that our function has to behave more like a polynomial. That means on the end it has to go up or down, or on this end it has to go up or down. So I'm going to put that here. It means on the left it goes up or it could go down. In the middle we still don't know, and on the right it could go up or it could go down. So we don't know which of these cases it is, but we know it does one of these. It either goes up on the left, down on the left, or it goes up on the right, down on the right. That's what happens when your numerator is bigger than your denominator. Does this seem complicated already? Okay, and the last case, case C. Case C is what?
Numerator is equal to.
Yeah, if they're the same degree. So if numerator is equal to denominator, then we will have a horizontal asymptote. It won't be the x-axis. What it'll be is it'll be a line, a horizontal line that's either moved up or down, like it's going to be shifted. And the way we'll find it, just write this down, and when we get to it, I'll explain it, all right? We are going to have a horizontal asymptote, and it's going to be the equation y equals the LC of the numerator divided by the LC of the denominator. What do I mean by LC? Leading coefficient. So we talked about that with polynomials. That's your case C. All right. So step 4 is new, it's weird, it's got different cases. I'm going to have to show you an example of each one. All right, so backtracking. Step 1, is it a rational function? Step 2, X intercepts, set the numerator equal to 0. Step 3, find the vertical asymptote, set the denominator equal to 0. Step 4, find the horizontal asymptotes if they exist. We have to look at the 3 different possibilities. We either have one at the x-axis, we don't have them, the left and right sides go up or down, we don't know, or we have one but it's just a line that's shifted up and down. We somehow have to look at the leading coefficients of the numerator and denominator. Yes?
So here when we set the denominator like, 0,
Yes.
the outcome will be defined, isn't it?
It would be what?
The number over 0 is like, isn't it defined?
It is, but that's where we're going to have those vertical dotted lines.
Yeah.
It's telling us where those are going to be.
On the other side also, when we set the denominator 0, that means we get the outcome is going to be 0.
When we set the denominator,
The denominator.
this one right here, or this one?
No, that one is at the time we see.
Uh-huh.
When we set the denominator, like
Numerator, the top one.
yes.
Yes.
So we set it to 0, the outcome is going to be 0.
Which means we're on the x-axis,
Yes.
right? Which means that our y value is 0, which means we are at an X intercept. Okay? Here, let's do something. Go back to step 2. Okay? And on step 2, I want you to write at the very bottom that your answers are points on the graph, on the x-axis. Okay, so what was step 2? Is finding the x-intercepts, right? So you solve that equation. Whatever answers you get are going to be points that are on your x-axis. All right? When you go and do step 3, your answers are not points. These answers are vertical dotted lines, barriers, right? Barriers for your graph, right? These are the things that your function is going to run into them and either go up or down when they get to them. Does that make sense? You're going to have to let me work through one of these to kind of get the full flavor of what's going on here. And when you get to 4, when you're finding the horizontal asymptotes, your answers here, if you have them, is a horizontal dotted line that acts like a magnet. Remember I said that? At the ends, it pulls your function towards it. We're still not done, okay? We're only on step 4. Okay, step 5 now? Ready for step 5? Okay, step 5 is we are going to plot all the information we have down on a graph. Okay, so we're going to plot all information that we have from parts 2 through 4. We want to get a general kind of picture of the graph. We have 2 more steps. Step 6 is to choose test points. I will explain this later as we do an example. All right? Choose test points, and then 7 is our last step, is the most exciting part of the whole thing, is to connect the dots. That's the fun part. All right. Ready to do it? Here we go. Another one of those Mondays where you come in here and I just, you had no idea how exciting this stuff would be, right? All right, let's go with that first one that I put up on the board. Remember, I gave us 3 examples. Let me see if I want that first one. Yeah, let's do that one. F of x equals 4x minus 8 over x squared plus 8x. Anissa, step 1.
Make sure it's irrational.
Is it? Okay, good. Step 2.
Find the x-intercepts.
So the x-intercepts. How do I do the step 2?